All right, let's go ahead and get started. Today we're going to sort of delve into a new topic with concrete, and that's looking at shear. Let me go ahead and get the sign-in sheet started. Okay, so this is a little different. For instance, one of the things I've been hammering into your head is things like, what is phi for beams? It depends. Well, that's for moment. For shear, it's 0.75. So, of course, I've got to change things up a little bit. But shear design, I think, is kind of nifty in the end. I think it can be kind of a fun endeavor. And it takes a fair amount of engineering judgment. You need to make sure that what you're specifying makes sense. But before we get into all that, I do want to take some time and actually review what's going on with shear and why it's important and all the mechanics associated, et cetera. So let's start off with this. If you left structural analysis unable to do this problem, I failed as a professor. A simply supported beam with a uniformly distributed load, I have got to believe you can do that, right? Moment diagram, WL squared over 8, all that jazz. Okay? We have hammered this problem to the ground, okay? We have done slabs, we have done beams, we have done rectangular beams, T-beams, doubly reinforced beams. We have done just about every beam problem that we can, okay? Now it's time to discuss shear, okay? Which you all probably need this. All right, so I think we've handled moment, as much as we can. Shear, on the other hand, we haven't touched. And you all should know from structural analysis that is something we have to deal with. I mean, shears are there. Now, one thing that is a little different, and we'll see this later when we get to this in steel design, it's funny how in steel design I really don't talk about shear very much, because the way that we manufacture rolled I-shapes in the United States, shear just doesn't, it really hardly ever matters when you're dealing with a rolled beam. What ends up happening in steel is you'll have like 20 kips of load in shear and like 200 kips in capacity. It's one of those things where shear just doesn't matter. In concrete, however, we have to do a fair amount of design for it. Now, the way that we resist shear forces in reinforced concrete is through shear stirrup layouts, as you see here. So what you've got here is an image of a typical rebar cage in a reinforced concrete beam. So you see here on the bottom, these are the tensile reinforcement beams that you already know how to select. Up top is the compression reinforcement that really mostly serves to tie the cage together, but you notice these sort of hoops that are circling the two sets of bars. These are called shear stirrups. It's basically just bent pieces of rebar that we lay in the beam. Now, one thing that might be kind of subtle right off the bat until you notice it, notice how they're more bunched up near the supports than they are in the middle. Notice that? That's because shears are higher at the supports than they are in the middle. So it stands to reason you should have more of them at the supports than you do in the middle. And largely that'll be the case. Okay? Now, what happens with shear? Let's go back to that wonderful world of Moore's circle. You all know about that, right? Remember, you've got a stress state in 2 dimensions, and you want to determine what the principal stresses are and the maximum shear stress and what have you. If you have a stress state that is under pure shear and you calculate your principal stresses, you will find 2 things. One, your principal stresses are equal and opposite, so you'll have some amount of tension and some amount of compression. And 2, when you look at that orientation, that rotation, it's at a 45-degree angle. Now, why the heck does that matter? Go down to the lab and put up a reinforced concrete beam and load it in shear and see what happens. What ends up happening is you get a failure mechanism that looks something like this. First thing to notice is see how that crack occurs right around, oh, I don't know, 45 degrees? That's number one. Number two, look at the failure mechanism. Okay, it was a crack, but the crack opens this way, right? See that? It's opening this way, which is the direction that we're seeing tension. Concrete, strong in compression, but it's weak in tension, okay? Make sense? If you look at shear buckling in steel beams, it's kind of the same phenomenon, only instead of, the material cracking, it buckles in the opposite direction because of the material being in compression. So, all right. So, make sense? All right. What's that? Oh, okay. When we compute our capacity, we go back to our fundamental LRFD ultimate strength design expression that the factored resistances must be greater than or equal to the factored loads. Now, our resistance is calculated as follows. We say that the nominal resistance equals the shear strength that's provided by the concrete plus the shear strength that's provided by the reinforcement. Seems to make sense, right? Everybody good? Okay. Now, because we're not dealing with different levels of ductility, if you will, for shear as opposed to moment. So with moment, our ductility was a direct function of how much steel we had and how much strain we were able to achieve. Phi changes. For shear, however, that's not really the case. We tend to get around the same amount of ductility regardless. So we accept a phi value of 0.75. All right? Now, in terms of shear strength, if we look at the concrete, it's pretty simple. The shear strength of concrete is constant, okay? And we calculate it as 2 times the effective area, B times D, times lambda, that lightweight aggregate factor, lightweight concrete parameter, and then times the square root of FC prime. So let's just make sure we're clear on a couple things. So lambda, remember it's 1 for lightweight concrete, it's like 0.85 for sand lightweight concrete, 0.75 for lightweight concrete in general. B and D are the beam widths and the effective depths. Square root of FC prime, remember, put in PSI, get out PSI. Remember that? All right. So if you calculate V sub C correctly, you should get an answer in pounds, okay? Because B and W are in inches, so that's inches squared. This is PSI, so it'll be PSI times inches squared. It'll give you pounds. Everybody okay with that? No. We've talked about this before. That's square root of FC prime. Remember, when you're dealing with square root of FC prime, that's that empirical model. You put in PSI, you get out PSI. Calculate that. You put in 4 as opposed to 4,000, you will get a different number. And I promise you it will be the wrong answer. It's an empirical model. We've discussed this before. So, sound good? Go ahead. Go. Tell you what, do the rupture strength. Do 7.5 times the square root of FC prime. Put in 4 and put in 4,000. Guarantee you get a different number. Because I'm right. All right. Now, is everybody okay with that? All right. Now, the shear resistance for the steel is a little bit different, okay? The way that we calculate that is we say it's the area of the shear reinforcement times the yield stress times this number N, which N is the number of bars per beam depth. So another way you could calculate that is the depth divided by the spacing, and we'll talk about that for a little bit. The idea behind N is that we assume, okay, we assume that the beam cracks diagonally, as follows. And that N value is basically, we're trying to determine how many stirrups are there in a given crack. So it's the depth divided by the stirrup spacing. Does that make sense? Okay. All right. Now here's another thing. A sub V. A sub V is the area of steel that resists shear, okay? Now, this is a typical shear stirrup layout. Let's say you've just got a typical U-shaped stirrup or a hoop-shaped stirrup that you see right here. If I cut a section through that crack, how many bars am I cutting through right here? Not one, but two. Does that make sense? So if I look up let's say they're number 3 stirrups, a very common stirrup size. If I look up a number 3 stirrup, the area of a number 3 is 0.11. My A sub V, however, would be 0.22. Does that make sense? And that's going to change depending upon your stirrup layout. This would be the area of 2 bars. This would be the area of 2 bars. This would be the area of 1 bar. This would be the area of how many? 4. All right. Does that make sense? Okay. Everybody good so far? Okay, so a couple notes. All right, so we do have a minimum amount of shear reinforcement that we are to provide, but that usually never becomes a problem. We also have maximum stirrup spacings that we have to deal with. That actually does tend to become a governing stirrup spacing near the end. When you do stirrup design, you tend to do your stirrup design based off of a minimum spacing and a maximum spacing. Your maximum spacing is a function of your shear strength of your steel compared to this upper limit of the capacity of the concrete. Sorry. Is everybody okay with this so far? We're going to do a couple examples to kind of illustrate this. It's not too bad. All right. Okay. This is actually kind of atypical in the world of concrete. A lot of times you aren't really asked in textbooks to analyze a beam's shear capacity, but I want to do that so that you all understand these procedures front to back. This is an important design process to learn, and arguably I think it's one of the things that's kind of an afterthought in structural design. I mean, a lot of times you're so focused on the moment, and then shear, let's just put some stuff in there. Now this stuff matters, okay? So I want to do a shear analysis problem. We've got 4 KSI concrete that's normal weight, 60 KSI steel. It's a 24-foot long beam. Number 3 stirrups are utilized. Here you can see the cross section. Notice I'm not really giving you any data about these 3 bars down here because I don't care. We're not looking at moment, we're looking at shear. Now this is 1.5 kips per foot dead load, 3 kips per foot live load. And here's the layout. Now what we've got here are a series of stirrup layouts, and I want you to kind of understand what this diagram means. So here's the center line of the beam. So all I'm showing you is the stirrup layout from a support to the center line, okay? So imagine on the other end like a mirror image, okay? Now we've got these multiple regions of stirrup spacings, which that's one thing I do want to point out. That is common to have multiple regions, because if you can shave the number of stirrups in a given beam, you might go, well, what does it matter if you had 20 stirrups versus 18? Does that really affect the economy? Well, if they're using 800 of those beams in a given building, yeah, that does matter. So this is a very important point to make. But at the same time, you also have to have a little bit of engineering judgment associated with it. You don't want to specify 8 different regions if all you're going to do is cut out 1 stirrup. You don't want to make it too complicated. So there's a little bit of give and take. You gotta. That's where that engineering judgment comes into play. Everybody okay? All right. We're going to break out some of them structural analysis skills that y'all learned last semester. All right, let's see. All right, let's see. Okay. Oh, goodness. I thought I fixed that. Hold on. Give me one moment. I thought I fixed that. It should have on my account. I'm confused why. Oh, and then okay. All right. So let's write down a couple parameters that are kind of important. Let's start off with some material constants. All right. So we've got, I'll say for the concrete, we've got FC prime is 4 KSI, and we said normal weight concrete. So that means that our unit weight is probably 150 pounds per cubic foot. And what's lambda? There we go. For the steel, we have Fy is 60 KSI. All right. All right. Now let's look at some of the beam geometry. Just make sure we've got all that written down. Okay. So this beam is, not 20, 24. 24 feet or 288 inches long. Okay. Let's see. We've got the width of the beam is, what is it, 12 inches? The depth is 24. The height is 27. Everybody see where I'm getting this? Okay. Now, we have number 3 stirrups. So the area of a number 3 bar is 0.11 inches squared. Therefore, the area in shear, or the area of shear reinforcement is, I'm getting ahead of myself, 0.22. So far, so good? All right. And then our loads. We don't know what the self-weight is. We're going to have to compute that. We know that dead load is 1.5, is it, kips per foot? And all right. Give you all a moment to sort of catch up. Everybody with me so far? Okay. So let's start off and let's do some, oh goodness, structural analysis. All right. So tell me this. How am I going to compute the self-weight of the beam? Times what? There we go. .15 kips per cubic foot times 12 inches times 27 inches, and then don't forget our units. And then that yields that. So therefore, W sub U, 1.2, and then plug and chug, and that should be about 7.005 or about 7 kips per foot. Oh, oh. All right. Okay, everybody good with this? All right, I'm going to go ahead and switch to the next slide. Do you need any more room or more time? Okay, all right. Oh, goodness, what the heck? Example, getting ahead of myself, thinking about later on. Okay. So what I want to do is look at this from a structural analysis perspective. This is a beam subjected to a uniformly distributed load. Is that correct? So we're dealing with a problem that looks like this. Actually, no, I'm going to lower this down a little bit. We have a beam. It's being subjected to some distributed load. I'm going to have some reaction here. Some reaction such that that length is L, so on and so forth. Everybody okay with that? What can I do with that distributed load? Turn it into a point load, and then we can say, all right, I've got this point load in the center. What's the magnitude of that point load? W times L. How far is it from the left? L over 2. There we go. Bringing it back. All right. Sound good? Okay. So we'll call this A. We'll call this B. I could say reaction at A and reaction at B, but I think we all know that those are both going to be equal. So we'll sum moments at A. All right. So summing moments at A, I have WUL times L over 2. I have R times L, right? So WL squared over 2 equals RL. R is WL. All right. Sound good? Now, you all should know enough by now that since I'm not really dealing with this from a units perspective, maybe I'll just do VU. What does the shear diagram look like for a problem like this? It looks something about like that, right? And this is a straight line, isn't it? So maybe what I want to do is try and define an equation for that line. Make sense? All right, is everybody with me so far? Okay. So now I'm going to cut a section. I'm going to use my secret weapon of structural engineering. So I've got my reaction, and keeping in mind, maybe I should scroll up here, I'm cutting a section at some distance where this is x, right? Some random distance, right? All right? And remember, inside the beam, I have some unknown shear and some unknown moment. I don't know what they are. Maybe we'll call it, to be consistent with our notation, maybe we'll call that MU and call this VU. All right? Now this distributed load is W sub U, and that distance is X. Y'all remember this stuff? We've done it. I know we have. All right. Sound good? Should I just draw a bunch of arrows on it? All right. Collapse that into a point load WU times X. Now, we can go ahead and put a distance and say this is X over 2, but it actually isn't going to matter because we just care about shears. Now, how do I determine that shear inside the cut? I just sum forces. Okay? So if I sum forces in the y direction, what do I have going up? I have WU L over 2. Going down, I have WU X and VU. So therefore, excuse me. So WU L over 2 is VU minus W or plus WU times X, or the following. Now, one thing I'll point out is this is the equation of a line. Okay. So far, so good. So, would you agree that this equation maps that line, right? Y equals mx plus b. It's a negative slope. It's going down, slope being WU, and the y-intercept being this term, which is R, WL over 2. Everybody good? Okay. Okay. So let's see. Where am I at? Okay. Okay. So let's look at the concrete capacity first, because it's constant. Now, to start off, how do we compute the capacity of just the concrete? It is 2 lambda BWD square root of FC prime. So let's plug and chug. 2 times what's lambda? What's BW? That's the beam width, right? What is the beam width for this problem? 12 inches, yep. D is 24 inches times the square root of what? 4,000. You put in PSI and you get out PSI. So this is going to give us V sub C in pounds. That comes out to be 36,429.4 pounds, or 36.43 kips. And while we're at it, we'll go ahead and compute phi VC, which is 0.75. And that comes out to be 27.32 kips. Now, off to the side, I want to make a point here, just so you all are aware. I'll put note. What is the maximum shear that this beam will withstand? It's the reactions, right? So I'll say VU max is the reaction, which is WUL over 2. What is W sub U? We already computed that. What is that? What is L? And what does that equal? What does that mean? Somebody tell me what that means. What? If we, well, let's put it like this. If we had no stirrups, what would that mean? What is phi VC. It is its strength. This is how much the concrete can withstand. I'm saying that it is being subjected to this much. We better have stirrups in this beam, otherwise we're going to have some problems. Which that's another thing about shear that I didn't mention. If you have a ductile beam, in moment, failure is kind of gradual. If you see a shear crack in a beam, you run, because that sucker's coming down, and it's coming down quick. Okay? When shear failure happens, it's very dramatic and it's very sudden. So if all we had was concrete and no stirrups in this beam, I would be running. And there's that really awesome t-shirt that says, like, structural engineer, if I'm running from a building, you better try and keep up. Just saying. So, all right, does that make sense? Everybody okay with this? Now, let me sort of, let's look at the steel capacity. Steel and beam capacity. All right, how many stirrup regions are there? 4, okay? So I'm going to put, I'll say, 4 regions total. Okay? Now, I am going to demonstrate the calcs for region 1, and then I'm going to tabulate everything else. All right. Does that make sense? All right, so region 1. What's the stirrup spacing in region 1? 4 inches. All right. So therefore, the first thing I'm going to calculate is VS. Okay? VS is the area in shear, or the area of shear reinforcement, FYT D over S, which is what? What's the area of shear reinforcement? There we go. Because we're dealing with a U-shaped stirrup. 60 KSI. And then 24 inches over 4 inches. So in this region, we're assuming that we have about 6 stirrups per crack. Okay, so that's a lot. Okay, so if you calculate that out, you're going to get a capacity of 79.2 kips. All right? Now, phi VS is 0.75 times that, which is 59.4. And phi VN is what? Phi VC plus phi VS, right? The concrete capacity plus the shear capacity. And I'm making it a point to be, consistent with my labeling, that I've got my phis, accounted for appropriately. So what's phi VC? 27.32 plus 59.4, and phi VN is 86. Oh, goodness, what happened there? Now, what does that mean? If I compare that to this. Yeah, so this right here, this is how much load is being applied. This is how much it can withstand. That's a little better, isn't it? Right? Before, if all we were dealing with, or if all we were able to count on was the strength of the concrete, we'd be having some problems. Does that make sense? Everybody okay with that? That would be bad. Yes. And we'll look at something here in a second that I think will clear this up. Okay. So I'll say for remaining regions. Typo, that's supposed to be kips. Okay, so walk me through this so that we're understanding what's going on here. Okay, so region number 1. Okay, now what I've got here is this range, and I'm going to say it's from 0 to 52. Now, do you all see where I'm getting that? Okay, and I'm going to pull that up because I want that to make sense. This region 1 goes from x equals 0 to x equals 52. Everybody okay with that? Okay. All right. What was our stirrup spacing in that region? 4 inches. And we got, what do we get for VS? We got 79.2, and we got 86.72 for that. Is that a fair statement? That's what we got, right? Now, I'm going to go ahead and do region 2. However, I want you to tell me what the range is. What's the range for region number 2? 52 to 84. All right. What's the spacing? Get that out of the way. All right. Now, if you do the math, you're going to get that this is 39.6. It's half of V sub S, which makes sense because the spacing is doubled. And then 57.02. All right. Region number 3. Tell me what to put there. 84 inches to what? Spacing is 10, right? Do the math. This comes out to 31.68, 51.08. Now, region number 4, what's the range? To midspan, which is 12 times 12. What's the stirrup spacing? No, well, one way of looking at it is there are no stirrups in that region. There's nothing there, right? So I'm going to put no. There's no stirrups there. And if there's no stirrups there, what's the capacity and shear for the steel? 0. So what is PVN? PVC, it's 27.32. So if I were to plot that, okay, if I were to say, we'll say X, and this is PVN, I would get a line that looks something like this. It would kind of be like a big stair step. From 0 to 52, I'd have a value. And then from 52 to 84, I'd have a value. From 84 to 124, I'd have a value. And then a value. Does that make sense? Everybody okay with that? All right. Can I go ahead and go to the next slide? All right. Because I want to show you something. So example. What? Yeah, I'm just, you know, if you, I demonstrated it for region 1, and it's the same thing, you know. Okay, so I'm going to put shear diagram. All right. Now your shear diagram, what is it? It's VU equals WU L over 2 minus WUX, or if I like doing less math, WU L over 2 minus X. W sub U is, what is it? It's 7.005 kips per foot. And then, what's that divided by 12? Somebody divide that by 12 for me. Kips per inch. And then length is 24 feet or 288 inches. Okay? What I'm going to do is I'm going to calculate what the shear force is at these different increments. So I'm going to look at the shear at 0 inches and 52 inches and 84 inches and 124 inches and 144 inches. Okay? So I'll do the first one. Okay? So the first one is, I would say, 0.584 kips per inch times 144 inches minus 0, and that's 84.06. Do you all see how I did that? I'm taking this equation and I'm plugging it in right here, right? So look, WU L over 2 minus X. See that? So the next one would be like 0.584 minus 52. Do that out to be 53.71. Do you all see how I'm doing that? It's an equation I'm plugging and chugging. So the next three, let's see, this one comes out to be 35.03. This one comes out to be 11.68. Anybody tell me what the third one, or the last one's going to be? 0. What? Yes. Yeah. Do you all see how I'm doing that? Any questions? All right, do you all need this up for a little bit? All right. You good? Okay. Let me show you something. Let me save this. And then let's look at this slide. Okay, so this is a slide that I plotted in Excel, and this is looking at the beam that we just did. So this red dashed line are the 4 regions of shear capacity. So for that first region, the capacity was like, what, 84.06, and then it went to like 50-some, and then a little lower, and then down to 20. Y'all are okay with that, right? Or the 27.3 or whatever. Okay, these are the shear capacities. Okay, This blue line is the shear diagram. Remember, it's linear, okay? So it's 0 at midspan and linear so forth. Notice how the capacity is always above the diagram. Everybody see that? That indicates that the beam is safe. All right. Does that make sense? Now what we're going to do, or next time, is we're going to learn how to design this beam. So with that, that's all I got. I will see you all next time.